Okay, welcome back everyone. I guess this is the first video of 2013, so we're going to start off by proving what Mr. Baker talked about in a previous video. Basically, we want to show two things. We want to show, first of all, that centripetal acceleration, AC, that it is a vector that points toward the center of a circle. And we're just talking about if we're going in a circular path. And we also want to show that the magnitude of the centripetal acceleration is equal to v squared over r. V is the speed and r is the radius of the circle. So v is the, sometimes we call this the tangential speed. In other words, how fast we're going tangent to the circle. Okay, so we'll start with the first one. And so I'm going to draw a chunk of a circle, and on the circle I'm going to draw two velocities. So let's say we're kind of moving sort of around the circle counterclockwise. So that means that at some starting time, maybe this is our initial position, we're going to have a velocity that's tangent to the circle at that point, so that's v initial. And then a short while later, not too much later, we'll have another velocity which is also tangent at a final point, and this is v final. And I want to make sure that v initial and v final have the same magnitude, but they point in different directions. So let's think about what we have to do to actually calculate acceleration. We know that acceleration is a vector, and we know that it's a change in velocity divided by a change in time. And we also know that any change is final minus initial. Okay? Now, one thing about this equation is that the delta t is a scalar, so that's not going to change the direction. So if we just look at the direction of v final minus v initial, that's going to give us the same direction as a, the acceleration. And keep in mind that when we are adding and subtracting vectors, that v final minus v initial is the same thing as v final plus negative v initial. Okay, so that means that we take our vector v final, and I'm just going to try to redraw it. So v final goes kind of sort of like this, pretty much, and we're going to add to that the opposite of v initial. So I'll draw it there, and then I'll just sort of grab it and drag it over to here. Okay? And then of course when we are done adding vectors, this is head to tail, alright? So if I have v final, okay, and negative v initial, head to tail, or v final minus v initial, otherwise known as delta v, is a vector that points kind of down and to the left. And if I take that vector and I put it in between, now you can see pretty clearly that the change in those two velocities points inward toward the center of the circle. So that's kind of our proof that if the change in velocity points inward, then so does the acceleration. Okay, so this is our proof that the centripetal acceleration points inward, and we can say that this is true because the change in velocity does. Alright, so that's the first part. The second part is to prove the magnitude. And to keep this video kind of short, I'm going to go through this a little bit quickly, so if you have to, just rewind. Okay, but this is based off a diagram that Newton drew. So pretend like you have a curved chunk of the Earth, and you fire something with some speed v, called v initial. Okay? So at the same time that it's going forward, it's also falling down. So I'm going to kind of stretch this out a little bit, and we're going to say that this is for a pretty small time interval delta t. Okay? So at the same time that it's moving forward, it's also falling down to the Earth. And we see this on Earth as a curved path. Okay, so let's say that right here is the actual center of the Earth, and maybe right there. Okay, so that means that this distance right here is the radius of the Earth, and this distance right here is the radius of the Earth. The only thing that we need to figure out is how far did it actually travel along this portion right here and along this portion right here. So for the first one, it's traveling with the speed v initial for an amount of time delta t. Let's just call that v delta t. Okay, the speed's not going to change, it's just going forward. And when it falls down to the Earth, well, that's gravity, right? We could write 1/2 gt squared. Whoops, I guess that would have to be delta t squared, right? But the thing is, it's falling towards the center of the Earth, wouldn't you agree? And so that is a centripetal acceleration. So we're going to write it as AC for acentripetal. Okay? So now what this does is it gives me a right triangle that has the legs v delta t, r, and then r plus 1/2 a delta t squared. So I just set up Pythagorean theorem, and so I have the hypotenuse, which is r plus 1/2 ac delta t squared. That whole thing is squared in the Pythagorean theorem. One leg is r squared, and the other leg is v delta t squared. Okay, now at this point, I'm going to kind of rush through some algebra, so if there's something that kind of makes you say, then just go back and try it yourself. So I'm going to take care of the left side first. So I'm going to have r squared plus 2 times r times 1/2, so it's just r ac delta t squared. Okay, that takes care of both of the middle terms, and then I'll have 1/4 ac squared delta t to the 4th. Okay, I think that works. And then over on the right side, I'm going to have r squared plus v squared delta t squared. I will just kind of distribute that. So I'm going to cross out r squared. It appears on each side. And I'm going to divide everything by a factor of t squared. So divide this by t squared, divide this, and divide this. Okay, so that one's gone, that one's gone. This one just turns into t squared. So what we're left with is r ac plus 1/4 ac squared delta t squared is equal to v squared. Okay, now this is the part that you might dislike a little bit, but I'm just going to ask you to believe me here. We're going to say that delta t is small. Not that it wasn't small in this step, but we're divided by the same thing. Delta t is really small. So small, as a matter of fact, that this entire term, because of the delta t squared, goes to 0. And because of that, we're able to write v squared is equal to rac. Oh, whoops, let's try this again. Let's write RAC is equal to v squared, so that means that centripetal acceleration has magnitude of v squared over r. And there it is. Okay, so I could have done this a couple of different ways, but this is the way that Newton chose to kind of derive it way back when. There's another way that's similar to the directional thing I did above, but I kind of like this method. And it shows us why the centripetal acceleration is equal to v squared over r. And of course you can check your units and notice that you're going to have meters squared per second squared divided by meters, which is going to give us meters per second squared, which is what we want for acceleration. So there you go.